a world so small and strange that even the laws of logic seem to loosen their ties a bit. Imagine, for a moment, that everything you can see, your chair, your hands, the moon, the stars, isn't made of solid stuff, but of patterns, waves, probabilities, humming softly beneath the surface of certainty. At our everyday scale, reality feels steady. A teacup falls, a coin lands, the lights turn on. But beneath that calm, in the world of atoms and particles, nothing behaves the way you'd expect. There, things can be in two places at once. They can vanish and reappear. They can decide what they are only after you've looked at them. It's a world that feels more like poetry than physics, but it's real. And it's what everything is built from. Picture yourself standing on that invisible frontier where certainty fades into shimmer. The air is still, but the silence vibrates. Each atom dances in a blur of maybe and maybe not. Light behaves like both a wave and a particle. Matter forgets whether it's here or there. It's beautiful, unsettling, and quietly funny that the entire universe depends on rules so bizarre we can barely describe them without sounding slightly confused. Before we step through the math and metaphors, I'd love to know where you're listening from tonight and what time it is, wherever you are. Maybe you're curled up under a blanket. Maybe you're on a train watching streetlights flicker past. Either way, it's a strange comfort, knowing we're sharing this little moment across the vastness. So dim the lights, let your thoughts slow down to the pace of probability and get comfortable. Because tonight, we'll ask some very small and very large questions. What is a particle, really? Does the universe exist when we're not looking? And why does light sometimes behave like it can't make up its mind? To find out, we'll have to go back to a time when physics felt complete, and one quiet German mathematician made a small adjustment to an equation that changed everything. Let's begin at the edge of certainty, that brief, golden moment before the universe decided to get weird. It's the late 1800s, and you're standing in a world where physics believes it's finished. The laws are written, the formulas polished, and every apple that falls, every orbit that turns, every spark that leaps, seems to obey with polite precision. You can almost hear the hum of confidence in the laboratories, the smell of ink, brass instruments, and arrogance mingling in the air. Newton's clockwork cosmos ticks reliably, each gear meshing with divine symmetry. Maxwell's equations have captured the ethereal dance of electricity and magnetism, wrapping lightning and radio waves into a neat mathematical bow. Even heat, that unruly chaos of motion, has been domesticated by thermodynamics. The universe, it seems, has been reduced to paperwork. The scientists of the age, with their stiff collars and starched certainty, glance around and see only refinement left to do a universe tidy enough to fit inside a textbook. But the thing about perfection is that it never lasts. Somewhere, beneath the equations, the universe is quietly giggling. Something doesn't fit. A faint whisper begins to ripple through the order, a hum no one can place. Experiments start producing results that don't behave. A shadow in the math, a flicker in the light. Somewhere between theory and observation, reality starts to twitch. Stars hum low, light begins to bend, order wavers, and rules pretend. Glass reflects. The glow misbehaves. Minds awaken. Certainty caves. You can almost picture it, a quiet lab in Berlin or Cambridge. Gas lamps flickering. A weary physicist staring at numbers that refuse to line up. The equations are fine, elegant even, but nature keeps whispering, "Nice try." Heat doesn't radiate quite as predicted. Light doesn't shine exactly as it should. Something small, almost trivial, begins to misbehave. The old guard shrugs it off. A rounding error, they say. But the younger scientists lean closer to the noise. Curious, atoms stir. The calm begins to sway. Whispers rise, and truth runs away. Mirrors hum, equations sigh, sparks flicker, and reason lies. It's funny to think how complacent science had become, how sure it was that the universe had been solved. Just a few details left, they said, like a chef sprinkling salt on an already perfect meal. Yet beneath their feet, the foundations were beginning to shift, and if you listen closely, you can almost hear it, the tick of Newton's cosmic clock starting to stutter. Imagine you're there. The air smells faintly of ozone and ink. You run your fingers over a polished brass microscope, feel the steady vibration of machines, early motors, whirring with industrial pride. Outside, steam engines huff across continents, telegraphs sing across oceans, and the human race is convinced it has conquered mystery itself. The future feels mechanical, predictable, certain, but not for long. Light flutters, as if shy, shadows stretch, and theories die. Heat laughs soft, beneath the hand. Atoms whisper, "You misunderstand." A few experiments, small, inconvenient, easy to ignore, start whispering rebellion. Heated metals glowing the wrong way, electric sparks flickering at odd frequencies, patterns in starlight that defy expectation. These weren't cosmic revolutions, yet just murmurs, the kind of things respectable physicists sweep under the rug while finishing their tea. But the universe doesn't like rugs. It likes surprises. The truth is, this calm age of physics wasn't the end of discovery. It was the deep breath before the plunge, like the moment before a storm, when the air feels too still, too perfect. You can feel it in your chest, that strange tension between order and chaos. And then, somewhere in a quiet study, someone turns up the heat on a small piece of metal just to see what happens. The light it emits doesn't match the math. The calculations explode into infinity, and suddenly, the most stable field in science begins to tremble. Glass cracks quiet. Minds take flight. The known world fades into night. Numbers burn. The sky unspools. Truth bends softly, breaking rules. You sit back, blinking at the candlelight, wondering if you misread something. You didn't. The universe really is misbehaving. The equations don't just disagree, they scream. The clock ticks strange. The air feels deep. The cosmos stirs, and reason sleeps. Light flares faint. Time exhales. The calm before the quantum fails. Somewhere far above, stars shine the same as they always have. But down here, under lamplight and calculation, humanity's understanding of them has cracked open. The scientists don't know it yet, but they've reached the threshold of something entirely new. A place where certainty dissolves, where particles hum with mischief, and where observation itself begins to shape reality. The age of the clockwork cosmos is over. The universe is about to show its real face. Not mechanical, not predictable, but shimmering, dancing, and full of riddles. You can feel it, that quiet moment before the curtain lifts, the hush before the music starts. And just like that, the 20th century begins. It began, innocently enough, with heat. Physicists were trying to understand something simple: why things glow when they're hot. A piece of metal in a forge, a coal in a fire, the filament of an old bulb, all of them radiate light as they warm. Red, then orange, then white. The pattern seemed obvious, elegant, and surely explainable by the smooth, predictable equations of classical physics. But when scientists ran the numbers, something impossible happened. The equations predicted that as the temperature rose, an object should emit more and more energy at shorter wavelengths, especially in the ultraviolet range, and not just a lot more infinite energy. A glowing piece of iron, by the math, should have vaporized the lab, the city, and perhaps the laws of thermodynamics along with it. It was absurd, and yet the calculations were correct, at least, by the old rules. This embarrassing little disaster became known as the ultraviolet catastrophe, a name that sounds like a rock band, but actually marks one of science's most profound crises. Let's turn up the heat, literally. You're standing in a dim laboratory at the turn of the 20th century, surrounded by brass instruments, smoking pipes, and the faint scent of oil lamps and burnt dust. On the table before you glows a piece of iron, its edges pulsing red, then orange, then white. Simple, beautiful, and as it turns out, utterly disastrous for physics. Physicists thought they had this one in the bag. When things heat up, they glow. The hotter they get, the brighter the light, and the higher the frequency. It's the kind of question that feels like an after-dinner exercise for scientists who've already solved the universe. Predictable, harmless, maybe even a little boring, so they started calculating. And that's where everything caught fire, metaphorically at first, but almost literally soon after. Using the proud equations of classical physics, they tried to predict how much light a hot object would give off at each wavelength. The math looked smooth and obedient, right up until the part of the spectrum no one could see, the ultraviolet. And there, at those tiny high-energy wavelengths, the numbers went berserk. According to the equations, a warm object should produce infinite energy, infinite heat, infinite light, which, of course, would mean every warm cup of tea should vaporize the universe. This absurdity became known as the ultraviolet catastrophe, a phrase that sounds like a prog rock album, but really just marks the moment classical physics melted under its own equations. The catastrophe wasn't in the stars or the lab, it was in the math itself. A polite reminder from nature that our theories, however tidy, are not in charge. You picture the poor scientists staring at their results, blinking through pipe smoke. The room is hot, their ink smudged, their patience evaporating. They double-check the constants. They remeasure the temperatures. They flip pages, adjust coefficients, mutter in disbelief. But no matter how they rearrange the math, the result keeps shouting the same impossible thing: infinity. The more energy you pour in, the more chaotic it gets. The curve of emitted light shoots upward like a runaway rocket, never leveling off. Every physicist who looked at it felt the same uneasy chill, that sensation of standing on the edge of something vast and wrong. You can almost hear the whisper of disbelief echoing across Europe's scientific halls. How could something so simple, heat, break physics? It was embarrassing. Heat, after all, wasn't new or mysterious. Humans had been cooking with it, worshipping it, and occasionally burning down laboratories with it for centuries. And yet here it was, calmly destroying the most elegant theory ever written. In the classical view, energy could flow in any amount, continuous, smooth, like water pouring from a jug. But the ultraviolet catastrophe suggested otherwise. It hinted that something fundamental about light, heat, and energy was quantized, restricted to discrete steps. But that was madness. Nature, everyone believed, didn't deal in steps. It flowed. Imagine, though, if light weren't a continuous rainbow, but a staircase, each rung representing a precise chunk of energy, no more and no less. It's a wild idea, but in hindsight, That's what the universe had been trying to tell us all along. Still, in this moment, in this glowing laboratory, with that stubborn piece of metal gleaming on the table, no one knew that yet. They only saw the failure. The equations that once described the heavens now collapsed under something as humble as a forge. The catastrophe spread like gossip through the scientific world. Infinite energy, one physicist joked nervously, is a rather poor design choice for a universe. Others muttered that perhaps the experiment was wrong, or that maybe light was playing a cruel trick. But the universe wasn't misbehaving. It was revealing something deeper, something so subtle that only the equations could see it. In the dark, that piece of metal kept glowing, not caring about anyone's confusion. It pulsed steadily, red to orange to white, releasing energy in ways no human formula could explain. And yet, hidden within that light, buried under the ash of failure, was the seed of something extraordinary, a new physics waiting to be born. Soon, a quiet man in Germany would look at these same numbers, sigh, and take a desperate mathematical gamble. He'd fix the catastrophe, but in doing so, he'd unravel the universe's last illusion of certainty. The heat, it turns out, was only the beginning, because sometimes, when the math explodes and the logic breaks, the universe is just clearing its throat, preparing to tell you something you've never imagined before. Max Planck wasn't a revolutionary. He was a tidy, careful German physicist who liked his numbers neat and his universe logical. He wasn't trying to upend the laws of nature only to patch a hole in them. The ultraviolet catastrophe was an embarrassment, a mathematical leak in an otherwise watertight theory. So, in 1900, Planck sat down not to reinvent physics, but to make the equations behave. His solution was quiet, almost absurdly small. What if, he suggested, energy couldn't be emitted in just any amount? What if it came in tiny, indivisible packets like coins you couldn't break or split? Each packet's size would depend on the frequency of the light, and there'd be no fractions allowed. He called these little bundles quanta. It worked. The infinite energy nightmare vanished. The math clicked into place. The curves matched experiment, and physics breathed a sigh of relief. Planck had done it. The catastrophe was cancelled. And yet, he couldn't quite bring himself to believe what he'd done. To him, quantization was a mathematical trick, not a revelation. He even described it as an act of desperation. After all, who would believe that the universe, so smooth and continuous to our eyes, actually runs on a cosmic grid of tiny, indivisible jumps? Let's move now to the man who didn't mean to start a revolution. Max Planck, the physicist who politely repaired the universe and accidentally broke reality. You can picture him in 1900 Berlin, methodical, dignified, the kind of man who aligns his pencils before beginning to think, his beard trimmed, his spectacles spotless, his office filled with ticking clocks and the faint smell of coal smoke. He wasn't looking for glory. He was looking for closure, a way to make the numbers stop screaming infinity every time heat met light. Planck believed the universe was elegant, rational, and perhaps a little German in temperament, orderly, disciplined, punctual. So when the ultraviolet catastrophe appeared, it must have felt like discovering that the laws of physics had left their socks on the floor. He couldn't stand it. He didn't want to rewrite the universe. He just wanted it to behave. He sat at his desk, the winter light grey and precise, and stared at the equations that mocked him. Every attempt to calculate the colour of glowing heat, red to orange to white, ended in absurdity. The math refused to fit the data. Energy, it seemed, was not flowing smoothly as it should. Somewhere, something was leaking. And then, in what he later called an act of desperation, Planck did something radical, though, at first, it didn't feel that way. He made a small adjustment, a mathematical patch, a cheat so subtle you could miss it entirely. He suggested that maybe, just maybe, energy wasn't continuous. Instead, it came in tiny, discrete packets, little bundles he called quanta. That's it. That's the moment the universe flinched. Energy, according to Planck, could only be emitted or absorbed in these fixed amounts. No fractions allowed. Like coins, not fluid. Steps, not slopes. It wasn't that light could take any value it wanted. It had to pay exact prices at the cosmic counter. And suddenly, the impossible curve of the ultraviolet catastrophe flattened neatly into reality. The numbers matched the experiments. The equations stopped exploding. Infinity was fixed. Planck must have sat back in quiet relief, the satisfaction of a craftsman who has finally coaxed a stubborn mechanism into working order. He had patched the leak, restored the dignity of physics, and probably gone home that evening for a well-earned dinner, thinking, that's that. Except it wasn't, because what Planck had proposed was not a repair, it was a revolution wearing a lab coat. The idea that energy came in indivisible chunks was absurd by classical standards. Nature wasn't supposed to jump, it was supposed to flow, but Planck's math left no room for argument. The quantum worked. He didn't quite believe his own idea. For years afterward, he treated it like an ugly cousin, necessary but embarrassing. A purely formal assumption, he called it. A mathematical trick. He hoped someone would find a more respectable explanation, but no one did. Instead, the trick began to spread, because that tiny word, quantum, didn't just fix one equation. It cracked open an entirely new way of seeing reality. Suddenly, light wasn't a smooth wave, but a collection of discrete energy packets. Matter, too, began to show hints of this strange, step-like behavior. The walls between the continuous and the quantized between classical and cosmic began to crumble. It's a strange image, isn't it? A quiet man in a waistcoat, sitting at his desk, accidentally detonating the foundations of physics. You can almost hear the gears grinding as the universe adjusts itself to this new rhythm. No longer a perfect clock, but a ticking one, quantized, pulsing, made of beats. Imagine holding a violin and discovering that the strings can only play certain notes, not because of your fingers, but because of the structure of the universe itself. That's what Planck had found. The grain of reality, the pixels of existence. He'd set out to tidy up a theory and ended up discovering that nature runs on a cosmic grid, an invisible staircase of energy, each step spaced by an amount now called Planck's constant. It's small, absurdly small, but in that tiny number lies the entire future of quantum mechanics. And so, with quiet precision and no intention of grandeur, Max Planck became the father of the quantum world, the man who fixed infinity, and in doing so, made the universe forever uncertain. He didn't know it yet, but in the glow of his equations, the next century of physics was already waking up a century where particles would refuse to stay put. Light would act like both wave and bullet, and certainty itself would melt like snow under the strange new sun of the quantum age. For centuries, light had been the polite guest of physics, predictable, mathematical, well-behaved. James Clerk Maxwell had shown that it was a wave, a beautiful ripple of electromagnetic energy, and everyone was content to leave it at that. But then, early in the 1900s, the universe began acting moody. Scientists noticed something peculiar when they shined light on certain metals. The light would sometimes knock loose tiny particles, electrons, as if it were nudging them free. That was fine, except for one infuriating detail. It only worked if the light had a high enough frequency. No matter how bright a low-frequency light was, it couldn't budge a single electron. But a faint beam of higher frequency light could kick them loose instantly. According to the wave theory, this made no sense. A brighter wave should have meant more energy, more oomph, more electrons flying out. But nature wasn't cooperating. It was as if light were a very picky locksmith, opening the door only when it struck the metal with the right kind of note, not just a louder one. That's when Albert Einstein, a young patent clerk with a soft spot for impossible questions, stepped in. He took Max Planck's strange little idea about quantized energy and made it bolder. What if light itself was made of those energy packets? Not continuous waves, but tiny, discrete bundles, photons. Let's step into the early 1900s, a time when light was still a gentleman, predictable, graceful, the sort of phenomenon that wore a monocle, held the door open for equations, and always arrived at the speed of, well, itself. For centuries, light had been the poster child of good physics, a model citizen that obeyed every rule in Maxwell's grand electromagnetic symphony. It was a wave, a vibration, rippling elegantly through the ether, smooth, continuous, civilized. But then, one day, light threw a tantrum. It began, as most revolutions do, with something small and annoying: metal surfaces. Scientists were shining light on bits of polished metal, watching how it knocked loose tiny electrons, like cosmic billiards. This was called the photoelectric effect, and according to classical physics, it should have been simple. The brighter the light, the more electrons it should eject, a gentle wave of energy washing over metal, kicking out electrons in proportion to its brightness. But that's not what happened. When low-frequency light, say, red, shined on the surface, no electrons moved, no matter how bright it was. You could crank up the intensity until your lab glowed like a toaster, and still, nothing. But the moment you switched to higher frequency light, ultraviolet or blue electrons jumped free instantly, even if the beam was faint. It was as if the metal had suddenly grown picky, only responding to the right kind of light, like a lock that only opened to one specific song. The universe, it seemed, had a playlist. Physicists were baffled. If light was a wave, its energy should depend on its intensity, not its color. Waves, after all, don't care about pitch. They care about amplitude. Louder waves should have meant stronger effects. But here was light, stubborn and theatrical, breaking all the rules of polite wave behavior. Enter Albert Einstein, a young patent clerk with wild hair, sharp eyes, and an instinct for heresy. While the rest of the world was still admiring Planck's mathematical trick, Einstein decided to take it seriously, maybe too seriously. He proposed something outrageous. What if light wasn't just a wave? What if it also behaved like a particle, a stream of tiny energy packets, or quanta, each carrying a specific amount of punch depending on its frequency? In this view, brightness didn't matter, frequency did. Red light simply didn't have enough energy per photon to knock an electron loose. But blue or ultraviolet light, each photon carried enough oomph to give electrons a proper shove. Einstein's idea was so absurd, it circled back to genius. He took the most elegant wave in physics and broke it into discrete, jittering bullets of energy. Suddenly, the photoelectric effect made sense. The lock had a key, not a continuous wave, but individual particles with just the right kick. Still, the implications were unsettling. For centuries, light had been one of the most understood things in science. Now it was behaving like a double agent, both wave and particle, depending on who was watching. You can imagine the discomfort this caused. Classical physicists rubbed their temples and muttered, "Surely he's mistaken." They preferred their light pure, predictable, and mathematically obedient. But experiment after experiment confirmed Einstein's audacity. Light could knock electrons loose, but only in packets. And so, the cracks deepened. Einstein himself must have smiled quietly at the irony. The man who had just introduced randomness to physics would later spend decades denying it. But for now, he had solved the unsolvable. Light wasn't misbehaving, it was simply revealing that the universe spoke a language richer and stranger than anyone had realized. Picture yourself in that laboratory, the air thick with pipe smoke and confusion. You can smell the ozone from the glowing filaments, hear the soft ticking of instruments. Each time you flick on the lamp, electrons leap like startled cats, but only if the color is right. You don't yet know it, but you've just witnessed the birth of the quantum photon, the first tiny messenger of a universe that refuses to pick a side. Waves or particles, continuous or discrete, polite or chaotic? The answer, it turns out, is yes. The light in your lab fades slowly, flickering through red and gold as the bulb cools. Outside, snow falls in the quiet streets of Bern. And somewhere inside the universe, a photon grins both a ripple and a bullet, a wave and a wink. Light, once the most well-behaved of all things, has broken curfew, and physics will never sleep soundly again. If you were to ask light to pick a side, are you a wave or are you a particle? It would probably shrug, shimmer a little, and answer, yes. For centuries, scientists tried to force it into one box or the other, but light never quite cooperated. It bent and rippled like a wave, scattering into rainbows and patterns of interference. But it also struck metal surfaces and kicked out electrons like a volley of tiny bullets. It was maddening. Waves and particles were supposed to be opposites, the difference between a whisper across water and a pebble skipping through it. Yet light behaved like both, depending on how you looked. The universe, it seemed, didn't care about our categories. It preferred contradictions. Einstein's photoelectric effect had cracked the door open. Light could act as a particle, but other experiments refused to let go of its wave nature. It diffracted, interfered, and danced through slits like ripples on a pond. And so physicists were left with a kind of cosmic identity crisis. Imagine trying to describe something that is everywhere and nowhere, continuous and discrete, real, but only when observed. That's what light forced scientists to do. It wasn't that the universe was misbehaving. It was that we'd been asking the wrong questions. Let's step into the moment where science itself looked in the mirror and the reflection winked. You're in a dimly lit lecture hall, early 20th century, surrounded by blackboards filled with tangled equations and professors muttering in disbelief. On one side of the room, you have the wave theorists, proud and traditional. On the other, the particle camp, defiant and smug. In between, a beam of light, calmly refusing to choose sides. For centuries, everyone agreed light was a wave, a beautiful, undulating ripple traveling through space. It bent around corners, diffracted through slits, and made rainbows from raindrops. Waves explained everything until they didn't. Because sometimes, light hit things like it had elbows. It bounced off surfaces, knocked electrons free, and refused to smear itself smoothly, as waves should. So physicists did what physicists do best when confused. They argued loudly and built more experiments. And the universe, ever mischievous, decided to play both sides. Picture it: a beam of light passing through two narrow slits and landing on a screen behind them. If light were made of particles, you'd expect two neat stripes, one behind each slit. But instead, you get a delicate interference pattern, dark and bright bands, overlapping like ripples on water. Waves, clearly. Light behaves like a wave. Until you dim it, you turn down the brightness, letting the light trickle through one photon at a time. Little bullets of energy, fired slowly enough that they couldn't possibly interfere with each other. You wait, breath held, as each photon hits the screen. They land one by one particle behavior, right? But over time, as the dots accumulate, the interference pattern still appears. It's as if each photon has been consulting with a ghostly version of itself, whispering, "You take that path, I'll take this one." Wave or particle. Both, apparently. This wasn't just a scientific puzzle, it was an existential one. Light had become a mirror for human confusion. If observation could change its behavior, what did that say about reality itself? Was the universe solid, or did it only decide what it was when someone looked? You can imagine the frustration. Classical physicists, raised on Newton's certainty, stared at their chalkboards like betrayed lovers. Their universe was supposed to be neat, deterministic, and logical. But here was light shimmering, smirking, doing the quantum equivalent of jazz. If you listen closely, you can almost hear it. Are you a wave? Yes. Are you a particle? Yes. Are you messing with me? Yes. The truth was both comforting and horrifying. Comforting because the math worked. Quantum mechanics could predict results with astonishing accuracy. Horrifying because it shattered the illusion of common sense. To make peace with it, physicists invented the idea of wave-particle duality. It's the cosmic equivalent of saying, "Don't worry about it." Light, and eventually all matter, simply is both a wave when you look for waves, a particle when you look for particles. Observation doesn't just reveal the truth, it decides which truth you get. It's absurd, poetic, and perfectly quantum. Think of it like this. Imagine you're trying to photograph a cat that won't sit still. Every time you aim your camera, it either stretches into a blur, wave, or freezes into a sharp point, particle, depending on how you focus. You can't catch both at once. The cat isn't misbehaving your way of seeing shapes what it becomes. That's the universe in a nutshell. Even Einstein, who introduced the concept of photons, grew uneasy with this paradox. He loved math that was clean, predictable. This was jazz, played by nature itself, improvisational, wild, indifferent to expectation. God, he said, does not play dice. But the universe just kept rolling them, softly, with a smile. By the time the debates settled, if they ever really did, light had rewritten the script for everything else. Electrons, protons, atoms, all of them began to show the same double life. The very matter you're made of hums with this duality, existing in waves of probability until observed. So the next time you see sunlight glinting off water, remember, what you're seeing isn't just light behaving beautifully. It's light deciding who it wants to be, a ripple, a particle, or both, depending on whether anyone's watching. Because in the quantum world, even photons have an attitude. They won't fit into your neat little boxes. They shimmer between them, unapologetically a reminder that the universe, deep down, might not care about categories at all. Wave, particle, paradox, and somewhere in between, you trying to make sense of it, while the light on your skin quietly laughs. Two slits, a beam of light, a piece of cardboard. It sounds like the kind of experiment a bored child might invent on a rainy afternoon, and yet it became one of the most bewildering discoveries in all of science. Because what those two slits revealed wasn't about light or metal or even vision. It was about reality itself. Here's how it goes. You shine a beam of light at a barrier with two narrow openings, and you watch the pattern it makes on a screen behind them. If light were made of particles, you'd expect to see two bright bands, one behind each slit, like twin rows of marbles. But instead, something beautiful appears, a pattern of many bright and dark stripes, like ripples overlapping on water. That's interference, a wave phenomenon. Light was acting like a wave again. So far, so strange, but manageable. Then came the twist. Scientists turned the light down, sending it through one photon at a time, one tiny particle of light after another. You'd think the interference would vanish, right? Each photon should pick a slit and go through. But no, after thousands of photons had passed, the interference pattern returned, as if each photon somehow traveled through both slits at once and interfered with itself. That's when physicists did what physicists do best. They panicked quietly and built detectors. We'll just measure which slit it goes through, they said. But when they did, the pattern changed. The moment they observed the photon, the interference vanished. The wave collapsed into neat, obedient particles again, as if light, embarrassed at being caught, straightened its tie and pretended nothing weird had happened. Turn off the detectors, and the waves returned. Turn them on, and the pattern vanished. The only difference was the act of looking. The experiment didn't just challenge physics, it challenged philosophy. Did observation actually change reality? Was the photon aware of being watched? Or did the act of gaining information itself alter the outcome? Nobody knew. All they could say was that when left alone, nature behaved like art fluid, uncertain, full of possibilities. And the moment we tried to pin it down, it solidified into something measurable and tame. Let's dim the lights, take a breath, and picture the setup. A flashlight, a piece of cardboard with two narrow slits, and a blank screen behind it. That's all. Simple, almost childish. The kind of experiment you could make in your garage with tape and curiosity. And yet, behind those two tiny openings lies one of the strangest truths ever uncovered. A quiet rebellion against everything you thought reality was. You shine the light. Two slits, one beam. What you'd expect are two bright lines on the screen, one behind each slit, like shadows of the openings. But instead, you get something beautiful, an interference pattern, a series of alternating bright and dark bands, like ripples from two stones, dropped in water, overlapping and cancelling each other out. The signature of a wave. Light, once again, is proving it's a wave. So far, so classical. The universe is behaving politely. But now, in true physicist fashion, someone asks, what if we send the photons one at a time? One little quantum of light, trickling through the setup like raindrops through a drain pipe. Surely now we'll get two simple bands particles going through one slit or the other, right? Wrong. The photons arrive on the screen one by one, tiny pinpricks of light, and at first, they seem random. But as they accumulate thousands, then millions, the interference pattern appears again. The same delicate stripes, as though each photon somehow passed through both slits at once and interfered with itself. Let that sink in. Each individual photon seems to travel through two paths simultaneously. It behaves like a wave, splitting and spreading until it hits the screen, where it collapses into a single point, like a particle caught pretending to be mist. You can almost hear the universe giggling. Physicists, naturally, were not amused. "All right," they said. "We'll just watch the photons. We'll place detectors at the slits to see which one each photon actually goes through." And when they did, the pattern vanished, the interference disappeared, the delicate wave-like dance collapsed into two simple stripes. Observation had changed the outcome. The very act of looking made the universe choose a side. Turn off the detectors, and the interference returns. Turn them back on, and it's gone again. The only difference? You're watching. It's as if the photon, in some unfathomable way, knows when it's being observed. It's not a trick of instruments or human error. The experiment has been repeated countless times, with light, with electrons, even with entire molecules. And the result is always the same. The moment measurement enters the picture, the universe changes its script. You might think, all right, maybe the detectors are interfering physically with the photons. But no, even when the detectors are as gentle as possible, even when the data is erased before anyone sees it, the effect persists. The photon behaves differently simply because information about its path could, in principle, exist. It's not the measurement itself, it's the possibility of knowledge. That's the part that still keeps physicists awake at night. Imagine reality as a great, shimmering field of potential countless possibilities vibrating together. Every particle, every photon, exists in all the ways it could exist, all at once. But the moment someone asks a question, the field collapses into a single answer. The act of observation doesn't just record reality, it creates it. It's unsettling, isn't it? To think that reality, at its core, may depend on attention. That the universe doesn't fully decide what's real until someone, somewhere, looks, and yet it fits perfectly with quantum mechanics. Every particle is described not by certainty, but by a wave function, a mathematical haze of probabilities. When unobserved, it spreads, explores, interferes. When measured, it snaps into a single outcome. The double-slit experiment simply made that strangeness visible. 2 slits, 1 beam, and the collapse of infinite possibility into something you can see. So here you are, in that dim lab, watching light behave like both mist and bullet, wave and particle, dream and fact. You feel the hair on your arms rise, not from fear, but from the realization that the border between out there and in here might not be as sharp as you thought. You blink, you think, you measure, and somewhere, in that instant, the universe blinks back. Because maybe, at its deepest level, the cosmos isn't a machine, it's a conversation, a dialogue between matter and mind, between what could be and what is. 2 slits, 1 beam, and reality, quietly deciding whether to be a wave, a particle, or both, depending on whether you're paying attention. If the double-slit experiment had a moral, it was this: the universe is shy. It doesn't reveal itself until you look, and when you do, it changes. Not by sleight of hand or cosmic prank, but through the cold, careful mathematics of quantum measurement. Somehow, the act of observation doesn't just record reality, it helps decide it. At first, physicists blamed the equipment. Surely the detectors were disturbing the photons, bumping them, influencing them, doing something physical. But the deeper they looked, the less comforting that explanation became. Even when the detectors were so delicate, they barely interacted at all. The same pattern appeared. It wasn't how they observed, it was that they observed. It was as if reality only chose a definite outcome once it realized it was being asked a question. Before that, everything existed in a hazy cloud of probabilities, waves of maybe. Only measurement collapsed the haze into a single, solid this. The photon wasn't here or there. It was here and there, until someone peaked. The equations supported it. They didn't describe objects with fixed properties, but wave functions, abstract shapes of possibility. The universe, on its smallest scales, wasn't a stage filled with actors. It was a script being written as the play unfolded, the ending changing every time an audience member turned their head. Of course, this made scientists deeply uncomfortable. Surely, they thought, the moon doesn't vanish when nobody looks at it. But the quantum world didn't care about comfort. It cared about coherence, the fragile state that exists only until information is exchanged. Once something is known, the wave collapses, the mystery folds, the story resolves, but only in that instant. Let's linger on that strange idea that the universe might, in some small way, notice you noticing it. It sounds like philosophy, or maybe something you'd read on the side of a candle in a gift shop. But it's not poetry, it's physics. The double-slit experiment didn't just show that particles behave differently when observed. It revealed that observation itself plays a role in shaping reality. Not through magic or consciousness beams, but through the subtle, iron logic of quantum measurement. At the heart of this mystery lies the wave function, the mathematical ghost that describes all the possible states of a quantum system. Before you look, the particle isn't here or there. It's everywhere it could be, a blur of probability. But the instant you measure it, that haze collapses into one specific outcome. The particle chooses, or rather, it's forced to choose a single version of itself. What's unsettling is that this isn't just metaphor, it's experiment. Over and over again, physicists have watched the universe make up its mind, only when asked a question. When unobserved, reality hums in superposition, existing in many states at once. When measured, it solidifies into one. It's tempting to think the observer's mind has something to do with it, but the math doesn't require consciousness, only interaction. The moment any part of the universe, a detector, a photon, a molecule gathers information about another, the wave function collapses. Observation, in physics, is just the act of knowing. Still, the implications are haunting. Every time you open your eyes, you're collapsing probabilities, not just recording the world, but quietly shaping it. You're not an outsider peeking at a pre-written script. You're a co-author, participating in the story as it unfolds. Of course, physicists have tried to downplay the drama. They'll tell you, gently, that observation doesn't mean human awareness, and that quantum measurement isn't mystical. It's just math. But even the math seems to carry a smirk, because no matter how hard you try to separate the observer from the observed, the universe refuses to let them part ways. You can't peel yourself out of reality, you're stitched into it. Imagine standing in a vast, dark theater. Before you is a stage of infinite possibilities. Every particle, every event, waiting in the wings. The curtain only lifts when you shine a light. And in doing so, you change the play. The actors adjust their lines. The scenery rearranges itself, and the show begins anew. Observation isn't passive, it's participation. Physicist John Archibald Wheeler put it beautifully. No phenomenon is a phenomenon until it is an observed phenomenon. In his view, the universe doesn't exist as a complete thing until measurement gives it form. It's not that your thoughts control reality, but that reality itself is unfinished until something interacts with it. That idea, the participatory universe, suggests that we live not in a world that is, but in a world that's becoming. Every experiment, every glance, every particle collision is another choice point, another act of creation. The cosmos, at its most fundamental level, is shy, not secretive, but sensitive. It responds. This doesn't mean the moon vanishes when no one looks at it. Sorry, Einstein. But it does mean that the very structure of reality depends on interaction. Every atom of you, every breath, every photon bouncing off your skin participates in this dance of knowing and being known. Maybe that's why we feel so drawn to gaze at the stars. Somewhere deep down, the act of looking connects us observer and observed in a cosmic feedback loop that's been running since the dawn of time. When you stare into the sky, in a very literal quantum sense, stares back. You can imagine the universe blushing under your attention, particles straightening their spin, photons aligning their frequencies, all pretending they weren't doing something weird just a moment ago. The cosmos isn't performing for you, it's becoming with you. And that, perhaps, is the quiet miracle hidden inside the math. The universe isn't indifferent, it's responsive. Every measurement, every observation, every fleeting act of awareness ripples outward, collapsing uncertainty into something real. So the next time you look at the world, the flicker of a candle, the glint of light on water, the faint hum of night, remember, you're not just seeing it, you're participating in it. And somewhere, far beneath the surface of things, the universe notices and rearranges itself, just a little, to say hello. Enter Erwin Schrödinger, soft-spoken, contemplative, a man who preferred equations to arguments and alpine hikes to applause. In the 1,920 seconds, the quantum world was a mess of paradoxes and half-finished theories, like a jigsaw with pieces from 3 different boxes. Schrödinger wanted clarity, something that could turn the strange behavior of particles into a language the universe might actually speak. What he came up with was, quite literally, music, the mathematics of waves. He imagined that a particle, instead of being a tiny marble darting around space, could be described as a wave that spread out, vibrating with every possible location and momentum it could have. Each point of that wave represented a probability, a measure of maybe. His masterpiece became known simply as the Schrödinger equation, and it gave quantum physics its pulse. It didn't tell you where a particle is, it told you where it's likely to be found if you look. It was as if the universe had replaced certainty with rhythm, an undulating field of possibilities, humming quietly beneath the visible world. In this new picture, an electron orbiting an atom wasn't a planet circling a sunday. It was a cloud, a shimmering blur of presence, sometimes here, sometimes there, never fully committed until observed. The idea felt almost mystical, and yet it worked with astonishing precision. Reality, it seemed, was less like a photograph and more like a symphony, a set of overlapping notes that only resolve into melody when someone listens. Schrödinger's equation didn't describe solid things. It described potential, dancing through mathematical space until something or someone forced the music to end. Of course, even Schrödinger wasn't entirely comfortable with what he'd unleashed, because if everything exists as a wave of possibilities, then what, exactly, makes it collapse into the single version we see? To wrestle with that question, he did what any good theorist does when facing existential dread. He put a cat in a box. Let's take a deep breath, crisp mountain air, if you like, because this part of the story begins with a man who loved both solitude and simplicity, Erwin Schrödinger. Picture him hiking the Austrian Alps in the 1,920 seconds, coat buttoned against the chill, his mind wandering somewhere between the clouds and the equations. Below him, physics is in chaos, a field fractured by paradoxes and half measures, waves and particles, probabilities and infinities, cats and headaches. The quantum world is a half-built house, and Schrödinger just wants to find the blueprint. He's not interested in philosophy or in endless debates about what light really is. He wants an equation, a clear, elegant rule that describes what matter does when no one's looking. And so, with the same patience you might bring to tuning a violin, Schrödinger begins to listen to the hum beneath reality. What he finds isn't a thing at all, it's a wave, but not a wave of water, or sound, or light, a wave of possibility. Each point of this wave represents where a particle could be a shimmering map of maybes, flowing and evolving through time. This wasn't just a clever metaphor, it was math, pure and predictive. He wrote it down, and the world would come to know it as the Schrödinger equation, the heartbeat of quantum mechanics. It looked almost simple. On one side, the rate of change. On the other, energy and curvature. But hidden inside was something profound. The idea that particles don't exist in definite places until something forces them to. They exist as wave functions, smooth, unbroken fields of probability that spread through space like ripples on an invisible ocean. If you were to ask where an electron is, the wave function wouldn't give you an answer. It would give you a song, a probability distribution, humming softly through the void, describing where the electron might appear if you decided to look. Before observation, it isn't here or there. It's everywhere it could possibly be, all at once. You can almost imagine it. Electrons as ghostly murmurs, their presence smeared across space like fog over a valley. Only when a measurement is made, when reality is asked a direct question, does the fog condense into a single droplet, one outcome pulled from an infinity of options. Schrödinger's equation didn't just describe this, it predicted it perfectly. It told physicists exactly how these quantum waves would behave, how they'd spread, interfere, and collapse. The accuracy was breathtaking. It was as if someone had discovered a hidden rhythm beneath chaos, a melody running through the atoms themselves. Still, Schrödinger felt uneasy. The idea that the universe existed as probability until observed was elegant mathematically, but emotionally disturbing. Where, then, was reality hiding? Was the moon a probability cloud when no one looked? Were people themselves quantum objects, existing in half-defined states of maybe until noticed by someone else? He didn't like those questions. He liked clean answers, crisp logic, but quantum mechanics refused to give him that luxury. His own equation implied that the universe was not built from definite things, but from potential, and that potential only becomes real through interaction. If Planck had cracked the door open and Einstein had peeked through, Schrödinger had stepped inside. He'd given the quantum world its mathematics, and in doing so, stripped it of certainty. You might think of the wave function as the universe's secret diary, not a list of events, but a catalogue of possibilities, constantly rewritten every time something happens. And because the act of observation changes the entry, no one ever reads the same version twice. In Schrödinger's hands, the cosmos became fluid, no longer a machine ticking predictably, but an orchestra of probabilities, improvising endlessly, never repeating a note. And yet, For all his brilliance, even Schrödinger couldn't escape the weirdness his equation created. Because if everything is a wave of possibilities, electrons, atoms, you, then the question becomes, what happens when you scale it up? What if something larger, say, a cat, were placed in this quantum blur? He probably smiled at the absurdity of it. And then, as all great physicists do, he turned absurdity into an equation. But that's a story for the next box, and the next paradox where curiosity meets cruelty, and the universe curls its paw beneath the lid. To make sense of the nonsense, Schrödinger reached for something familiar, something furry. In 1935, frustrated by how casually his colleagues spoke of particles being in multiple states at once, he decided to test that logic with an image no one could ignore. Thus was born the most unfortunate feline in the history of physics. Picture it, a cat sealed inside a box with a tiny vial of poison, a Geiger counter, and a single unstable atom. If the atom decays an event governed by pure quantum chance, the detector triggers, the vial breaks, and the cat dies. If it doesn't decay, the cat lives. Simple enough. But here's the catch. Until someone opens the box and observes, quantum mechanics says the atom exists in a superposition both decayed and not decayed, and therefore, the cat must be both dead and alive. It was never meant to be taken literally. Schrödinger wasn't planning a tragic pet experiment. He was making a point. The quantum rules that worked so beautifully for electrons and photons became absurd when applied to a living creature. Somewhere between atoms and cats, the math had to give way to common sense. But where, exactly, that boundary lay was anyone's guess. Inside that imaginary box, two worlds coexisted, one where the cat purred softly and one where it did not. Only observation would decide which reality we got to keep. Before that, the universe politely kept both on hold, as if reality were waiting for our RSVP. The thought experiment was meant to unsettle, and it did. It exposed the unease at the heart of quantum theory, that observation doesn't just reveal reality, it seems to create it. And if that's true, then the universe isn't just out there, running on autopilot. It's a strange conversation, one where even curiosity can change the ending. The cat became a symbol not of cruelty, but of the blurry border between knowing and not knowing, between potential and fact, between math and meaning. And as physicists argued about whether the cat was both alive and dead or neither, a young German scientist stepped forward to offer a humbler truth. Maybe we simply can't know everything. Let's open the lid slowly, carefully on one of the strangest thought experiments ever conceived. It begins not in a lab, but in the mind of Erwin Schrödinger, who, by 1935, had grown tired of the hand-waving and paradoxes that had become the new normal in quantum physics. Everyone was talking about electrons existing in superpositions, being in multiple states at once, both here and there, both particle and wave. That was fine when you were talking about subatomic specks. But Schrödinger, ever the mischief maker, decided to ask the question everyone else was avoiding. What happens when you scale that absurdity up? And so, he imagined a cat. A very unlucky cat. You're standing in his place now. Picture a perfectly ordinary feline, curious, whiskered, innocent of metaphysics being placed into a sealed steel box. Inside the box is a vial of poison, a Geiger counter, and a single radioactive atom. The setup is elegant in its cruelty. If that atom decays, the counter clicks, the mechanism breaks the vial, and the cat dies. If the atom doesn't decay, the cat lives. Now here's the kicker according to the mathematics of quantum mechanics. Before you open the box, that radioactive atom exists in a superposition of both decayed and undecayed states, which means the mechanism is both triggered and not triggered, which means the cat is both alive and dead. At the same time, Schrödinger didn't invent this story to be cruel to cats. He invented it to be cruel to physicists. He wanted to expose how bizarre the logic of quantum theory becomes when you apply it to the real world, a world of breathing things, of observers with eyelids and emotions. Because if the atom could exist in two states, why not the cat? And if the cat could, why not you? You can almost hear him pacing his study, cigarette smoke curling in the air, muttering to himself. Surely they see how ridiculous this is. He wasn't trying to prove quantum mechanics right. He was trying to show that it couldn't be the whole story. But here's the twist. Instead of disproving the theory, the cat proved its point. When you open the box, when you observe, the superposition collapses. The atom becomes either decayed or not. The cat becomes either dead or alive. Observation doesn't just reveal the outcome, it decides it. So in a way, the cat isn't both dead and alive for us. It's neither until we look. Reality is holding its breath inside that box, waiting for someone to peek. It's a haunting thought, isn't it? That existence might pause until acknowledged. That every unopened door, every unread message, every sealed box might hover in a kind of metaphysical limbo. Of course, no one ever built the cat box. It's a metaphor, but it's one that refuses to go away because it asks the question that physics still hasn't answered. When does the wave function collapse? Is it when a photon hits a detector? When a neuron fires in your brain? When consciousness itself notices? Schrödinger's cat became the mascot of quantum absurdity, purring or not, in the background of every conversation about reality. It inspired decades of debate and countless jokes. You've probably heard them. Schrödinger's cat walks into a bar and doesn't, or wanted, dead and alive. But beneath the humor lies an ache, the sense that we still don't quite know what real means. Physicists today interpret the cat differently depending on their camp. The Copenhagen interpretation says the cat is both alive and dead until observed superposed, suspended in potential. The many worlds interpretation says the universe splits. In one branch, the cat lives. In another, it doesn't. Reality doesn't collapse, it divides. Somewhere, out there, every possible version continues. But whichever view you take, one thing is certain. Schrödinger succeeded. He made the absurd impossible to ignore. Now, whenever we talk about quantum mechanics, about probabilities, observation, or measurement, we can't help but picture that poor, hypothetical creature sitting quietly in its box, embodying the question that refuses to die. Does the universe exist without witnesses? You close your eyes for a moment. You imagine the cat breathing softly or not. The box is sealed again. The air feels heavy with maybe. And somewhere, in that quiet, the universe smiles, half open, half closed, still waiting for someone brave enough to look. Werner Heisenberg was only in his 20s when he realized something deeply unsettling. Not about how the universe looked, but about how much of it we could ever know. He wasn't trying to mystify physics, he was trying to clean it up, to make sense of the strange new equations swirling around quantum mechanics. But the more precisely he tried to describe a particle's motion, the more the universe seemed to slip out of focus. The problem was simple, yet profound. To measure where a particle is, you have to interact with it. Shine light on it, bounce something off it, disturb it just enough to find out where it's hiding. But the act of measuring changes what you're trying to measure. The sharper you make the picture, the blurrier everything else becomes. Heisenberg put this realization into a principle so elegant and haunting, it still echoes through science today. You can never know both the position and the momentum of a particle with perfect accuracy. The more precisely you pin down one, the less you can know about the other. It wasn't a flaw in our instruments. It was the way nature itself worked, a built-in fuzziness woven into the fabric of existence. To older physicists raised on Newton's clockwork certainty, this sounded like heresy. Reality, they thought, must be precise. We just hadn't learned how to measure it yet. But Heisenberg showed that the uncertainty wasn't in the tools, it was in the world. At the smallest scales, nature isn't a series of definite events, but a spread of possibilities, narrowing only when observed. Reality wasn't hiding from us. It was inherently uncertain. And strangely, that uncertainty didn't break the universe. It stabilized it. It was the jitter at the heart of everything, the soft hum that keeps atoms from collapsing and matter from being too perfect to exist. In Heisenberg's world, not knowing wasn't failure, it was law. And for the first time, science had to accept that the deeper we looked into reality, the less certain it would ever become. Let's take a quiet step into the world of Werner Heisenberg, young, brilliant, and utterly exhausted. It's the late 1922, and he's sitting alone in a small cabin on a windswept island in the North Sea, trying to think straight while the universe plays tricks on him. His notebook is a battlefield of scribbled equations. His mind, a storm of contradictions. Everywhere he looks, particles refuse to stay still. The quantum world is a blur, not because his math is wrong, but because nature itself seems to insist on being mysterious. Heisenberg wasn't a mystic. He wasn't trying to turn science into philosophy. He was, if anything, trying to make sense of the mess left behind by Planck, Einstein, and Schrödinger, all these new, brilliant ideas that worked mathematically but made no sense conceptually. So, he asked the most practical of questions. What can we actually know about a particle? He thought of something simple, an electron moving through space. If you want to know where it is, you can shine light on it. But the moment you do, that light made of photons hits the electron and changes its motion. The more accurately you measure its position, the more you disturb its momentum. Try to catch it, and you bump it. Try to freeze it, and it slips away. It wasn't a limitation of instruments. It was a law of nature. Heisenberg realized that this fuzziness wasn't about bad data or clumsy hands. It was built into reality itself, an unavoidable trade-off between knowing where something is and how fast it's going. The sharper your focus on one, the blurrier the other becomes. He wrote it down as an equation, clean and merciless. Deltax times. Deltap is greater than or equal to 2. It looked simple, but it shattered certainty. The uncertainty principle was born. This wasn't the kind of uncertainty that made philosophers sigh or gamblers sweat. It was the fundamental texture of the cosmos. Reality wasn't made of neat, well-defined points following smooth trajectories. It was woven from probabilities, ranges, and limits of knowability. Nature, it turned out, values its privacy. You can almost imagine Heisenberg smiling sadly at that realization. He wasn't exposing chaos, he was revealing balance. The universe, in its quiet wisdom, doesn't let you know everything at once, not because it's cruel, but because knowledge itself has boundaries. And there's something oddly gentle about that. The universe isn't hiding things maliciously. It's whispering, you may know this or that, but not both. Choose. It's as if reality were saying, focus too closely on the details, and you'll lose the rhythm. Step back to see the whole, and the details will blur. A cosmic reminder that precision has a price, and that mystery is not failure, but a feature. When Heisenberg first presented his findings, even his colleagues struggled to believe it. Einstein protested. Schrödinger groaned. Bohr, ever the philosopher, simply nodded and said, "Yes, this makes sense." He saw that Heisenberg had found the missing heartbeat of quantum mechanics, a principle not of chaos, but of constraint, the rule that kept the universe from collapsing into absurdity. Because if everything could be known exactly, quantum particles would have no room to breathe, no way to exist as probabilities. The very act of limiting knowledge allows matter to remain flexible, creative, alive. Think about it, every atom in your body obeys Heisenberg's principle. Your electrons hover not in fixed orbits, but in clouds of probability, blurring gracefully around atomic nuclei. Without that uncertainty, chemistry wouldn't work, life wouldn't exist. Certainty, paradoxically, would destroy the world. It's humbling, isn't it, to realize that existence itself depends on a kind of built-in ambiguity, that the same law that frustrates physicists also allows stars to shine and neurons to fire. Heisenberg once said, "What we observe is not nature itself, but nature exposed to our method of questioning." He understood that science is not about domination, but conversation, a delicate exchange, where asking too hard a question changes the answer. So, when you gaze at the night sky, know this: the starlight reaching you carries within it the fingerprints of uncertainty. Each photon that touches your eye has been somewhere indefinite, part of a dance that no equation can perfectly describe. And maybe that's the lesson Heisenberg left us. Not that we should despair at what we can't know, but that we should marvel at what we can. The world doesn't need to be perfectly certain to be perfectly beautiful. In the end, uncertainty isn't an obstacle to understanding. It's the soft boundary that keeps knowledge humble and makes discovery endlessly possible. Albert Einstein loved order. His universe was elegant, curved space-time, graceful equations, light obeying cosmic speed limits. So when quantum mechanics arrived, all jittery and unpredictable, he was horrified. The idea that particles could behave randomly, that the universe itself might rely on chance, felt like heresy. "God does not play dice," he said, shaking his head at the new generation of physicists who seemed comfortable with uncertainty. To Einstein, randomness was just a placeholder for ignorance. Surely, there must be hidden variables, secret rules ticking quietly behind the scenes, invisible but precise. The universe, he believed, didn't gamble. It only looked like it did, because we hadn't learned the odds yet. But quantum physics didn't flinch. Experiments piled up, each confirming what the equations already whispered, that nature wasn't deterministic in the old sense. It didn't need hidden gears or unseen cogs. The randomness was real, built in, like static in the signal of existence. In this strange new world, a particle's path wasn't written until it was measured. Probabilities, not certainties, ruled. The universe didn't roll dice on a whim. It simply refused to show its hand until the moment you asked. Einstein argued with Niels Bohr for decades over this elegant debates between two giants of thought. Bohr gently reminded him, "Stop telling God what to do." And in time, the evidence sided with Bohr. Nature, it seemed, did play dice, though perhaps with rules too deep for us to ever read. It's a funny thought, really. Somewhere in the quantum fog, the universe might be tossing invisible dice, not to mock us, but to remind us that unpredictability isn't chaos, it's creativity. The cosmos doesn't deal in absolutes, it prefers possibilities. And whether or not God plays dice, The universe certainly enjoys a good mystery. Let's drift now into the ocean, not one made of water, but of energy. Picture it stretching endlessly in every direction, invisible, yet humming with potential. This is where modern physics finally learned to stop thinking of particles as marbles and start thinking of them as waves in a field. Because beneath the atoms, beneath even the quarks and electrons, lies something deeper, a restless sea from which everything rises. For years, scientists tried to describe the quantum world using familiar imagery: particles darting around like billiard balls, colliding and rebounding in predictable ways. It was a comforting picture, mechanical and tangible, but experiment after experiment ruined the illusion. Electrons interfered with themselves, photons vanished and reappeared, particles popped into existence, seemingly from nowhere, and vanished again, as if embarrassed to be caught. The universe, it seemed, didn't consist of things, but of happenings, ripples in a deeper, unseen medium. Imagine dropping a pebble into a pond. The ripple expands outward, elegant and smooth. But what if that ripple was the pebble? What if everything we call a particle is simply a wave traveling through an invisible ocean that fills all of space? That's quantum field theory. The idea that the universe isn't made of separate particles, but of fields vibrating everywhere, all the time. Each kind of particle corresponds to a specific field: an electron field, a photon field, a quark field, and so on. Where those fields ripple, we see particles. Where they are calm, we see nothing. But that nothing is never truly empty. Even the vacuum hums. You, right now, are a collection of waves in those fields. A brief, organized pattern of vibrations that thinks and breathes and occasionally worries about parking tickets. The atoms in your hand aren't made of solid stuff. They're standing waves in the quantum ocean, resonances that happen to hold together for a while before dissolving back into the sea. It's almost romantic, in a cosmic way. Everything you love, everything you see, is music played on the strings of the universe. In this view, a particle isn't born or destroyed. It's just a wave crest forming and fading, energy briefly borrowing shape. A photon is a tremor in the electromagnetic field. An electron, a localized oscillation in the electron field. Matter and light are simply two melodies played on different instruments. The equations of quantum field theory describe this dance in exquisite detail. They explain how particles interact, how forces emerge, how the vacuum itself buzzes with latent energy. But they also carry a kind of poetry. At its core, the universe is not built of bricks, but of beats. It also means empty space is anything but. What we call a vacuum is actually a restless froth, filled with particles flickering in and out of existence. Virtual particles, they're called, though there's nothing imaginary about their effects. They shape the structure of atoms, influence the behavior of gravity, and even determine how fast the universe expands. This is the world Planck and Einstein never saw coming, a cosmos alive with vibration, where reality is less about objects and more about oscillations. Imagine for a moment that you could tune your senses to hear the hum of this ocean. You'd sense a deep, steady resonance, not silence, but a kind of quantum heartbeat. Each particle that appears in your detectors, each photon that lands in your eye, is just a splash in that sea. And the strangest part? These fields don't exist in space. They are space. The universe isn't filled with quantum fields, it is one, a single fabric, rippling and folding into patterns we call stars, planets, and people. So when we talk about the awakening of the quantum field, what we really mean is this: physics finally opened its eyes to the fact that the universe isn't made of things moving through emptiness. The emptiness itself is alive. Even you, as a thought, as a voice reading this line, are a fleeting vibration in that grand field, a temporary arrangement of waves observing itself. And if that sounds strange or unsettling, maybe that's because it is. Because once you see the universe not as a machine, but as a shimmering, vibrating sea of energy, it becomes impossible to look at a quiet night sky and think of it as still. Nothing is ever truly still. Everything hums. The quantum field has always been awake. We just finally learned to listen. For a while, physicists tried to picture particles as tiny, tangible things, minuscule marbles zipping around, colliding, bouncing, behaving. But the more they studied them, the stranger they became. Particles could appear, disappear, or tunnel through walls. They could interfere with themselves, vanish from one side of an atom and show up on the other, as if space were less a stage and more an ocean. So, scientists changed the metaphor. Maybe particles weren't things in space. Maybe they were space, or rather, disturbances within it. Every electron, proton, and photon became a kind of ripple in a vast, invisible sea called a quantum field. It was an idea so radical, it made wave-particle duality look quaint. There weren't millions of individual particles out there, each with its own private life. There was just one continuous fabric for each type of particle. One field for electrons, another for quarks, one for photons, stretching across all of reality. When energy wiggles through that field, we perceive a particle. Imagine tapping your finger on the surface of a still pond. Each ripple is temporary, but the water remains. That's the universe at its most fundamental. Not a collection of billiard balls, but an endless ocean of energy, trembling slightly, never perfectly still. This vision became known as quantum field theory, and it quietly rewrote the definition of thing. A rock, a person, a planet, all just patterns of vibration, intricate standing waves in overlapping fields. Even the vacuum, that great cosmic nothing, wasn't empty. It seethed with invisible motion, full of virtual particles that flickered into existence, exchanged energy, and vanished again before anyone could notice. The universe, in this view, is not made of stuff. It's made of excitations. And you, sitting wherever you are not so much in the field as you are the field, arranged into the brief and beautiful shape of a person who happens, for now, to be alive. Let's imagine that truly you could clean the universe. You've removed every atom, every molecule, every grain of cosmic dust, every wandering photon. You've swept the galaxies from the room, wiped down space-time itself until it gleams. What's left, you'd think, must be perfect nothingness, absolute silence, a cosmic blank page. Except the universe refuses to give you silence. Even when you take everything away, it hums. The vacuum that's supposed nothing is never truly empty. It writhes with activity, an invisible storm of creation and destruction. Physicists call this the quantum vacuum, and it's one of the strangest ideas ever to survive serious science. In classical thinking, emptiness meant emptiness, no matter, no energy, no motion. But in the quantum world, nothingness behaves like an over-caffeinated toddler. It cannot sit still. Here's why. In quantum field theory, every field in the universe, the electron field, the photon field, the Higgs field, and all the others, is everywhere. Even when there are no particles, the fields themselves remain, like the surface of a calm ocean stretching to infinity. But calm in quantum mechanics doesn't mean motionless. The uncertainty principle forbids it. If the fields ever became perfectly still, we'd know their exact energy, and the universe doesn't allow that kind of precision. So, instead, even in the vacuum, they tremble ever so slightly. These tremors give birth to virtual particles, tiny, temporary bursts of energy that appear out of nowhere and vanish just as quickly. One moment they're there, the next, they're gone. You could call them borrowed energy, except that the universe is the kind of accountant that never lets its books go unbalanced. These fluctuations are allowed, as long as they repay their energy debt almost instantly. You can picture it like this. The vacuum isn't a flat, empty void. It's a quantum foam bubbles of existence, constantly flickering into being and popping out again. It's a sea of uncertainty, a background buzz that never stops. Even the deepest, darkest stretches of intergalactic space are full of this invisible fizz. And though these particles are fleeting, their influence is not. They tug on the fabric of space, shift atomic energy levels, and even help determine the strength of forces in the universe. When you feel warmth from sunlight, that light itself owes its existence to the same restless quantum vacuum that never sits still. Perhaps the most mind-bending part is that we've actually measured this nothingness. The Casimir effect is the proof. Put two metal plates extremely close together, only a few nanometers apart, and the quantum vacuum behaves differently between them than outside. Fewer fluctuations can exist in that narrow space, so the pressure from outside pushes the plates together. No external force, no electricity, just the vacuum itself. Squeezing, nothingness, it turns out, can shove things around. And if that doesn't make you reevaluate your definition of empty, nothing will. Even more astonishingly, this vacuum energy may be the key to one of the universe's greatest mysteries. Dark energy, the force driving cosmic expansion. When astronomers measure how quickly the universe is stretching, they find it's accelerating as if space itself is pushing outward. And what's the leading suspect behind that? The energy of the vacuum. It's possible that what we call dark energy is simply the cumulative effect of those countless quantum fluctuations. Every particle that pops in and out adds a minuscule nudge to the fabric of space-time. Individually, they're tiny. Collectively, they might be inflating the cosmos. Of course, there's a problem. When physicists calculate how much energy the vacuum should have, the result is mind-boggling, around 10 to the power of 120 times greater than what we observe. It's the largest mismatch between theory and measurement in all of science. Either the math is wrong, or the universe is performing a balancing act of cosmic proportions, cancelling most of its own energy so that galaxies don't explode. You could think of it this way. The vacuum is like a symphony orchestra where every musician is playing, but most of the notes cancel out, leaving only a faint, cosmic whisper. That whisper is what holds space together. So the next time you stare up at the night sky and see the empty darkness between the stars, remember this: it's not empty. It's alive with ghostly motion, a ceaseless murmur beneath existence. You're looking not into nothing, but into everything's foundation, the invisible hum that keeps reality from falling silent. Because in the quantum world, even nothing is something, and that something is restless, eternal, and impossibly alive. If you could somehow scoop out all the stars, dust, and atoms from a region of space, leave it completely bare, you might think you'd have nothing. But the universe doesn't do nothing. Even the vacuum, that great cosmic quiet, hums with restless energy. In quantum physics, Empty space is more like a seething ocean than a calm void. Beneath the silence, fields fluctuate wildly. Tiny pairs of particles and antiparticles pop into existence for the briefest moments, borrowing energy from the universe's balance sheet, then vanishing before the cosmic accountant notices. It sounds like cheating, but it's perfectly legal, as long as it happens fast enough. Physicists call this the quantum vacuum, though the term feels like an understatement. This vacuum is alive with jitter, a constant buzz of creation and annihilation. It's the background static of existence, always on, always whispering. Those virtual particles don't last long enough to be measured directly, but their presence can be felt. They nudge atoms. They tug on light. They even shift the energy levels of electrons, a subtle effect so real that we can measure it to astonishing precision. This invisible froth isn't just a sideshow. It shapes reality. The vacuum gives rise to forces, influences the structure of matter, and might even determine the expansion of the universe itself. What we call empty space carries weight literally. It's the stage and the script, and sometimes the actor, all at once. Imagine sitting in perfect darkness, in the quietest place imaginable. Even there, the emptiness would shimmer, not enough to see or hear, but enough to exist. Every cubic centimeter of space, no matter how barren, is bursting with energy, fluctuating endlessly, proof that the universe cannot help but create, even out of nothing. In quantum physics, nothing isn't a lack of something. It's the possibility of everything, waiting for a reason to appear. Let's begin where two particles are born twins from a single cosmic event, released together like a pair of sparks from the same flame. They travel in opposite directions, racing away into the dark. You could wait 1,000 years, let a galaxy spin between them, and still, impossibly, they would remain connected. Not by light, not by signal, not by anything you can see or measure, but by something deeper, entanglement. It sounds poetic, but it's science. In the quantum world, particles that interact can become so deeply linked that their properties spin, polarization, momentum are no longer individual. They form one shared system, even when separated by vast distances. Change one, and the other changes instantly. It's as if reality itself refuses to let them forget their shared past. Einstein, famously uncomfortable with such strangeness, called it spooky action at a distance. He didn't mean that as a compliment. He thought it was evidence that quantum theory must be incomplete, that there had to be hidden variables, invisible instructions tucked inside the particles from the start, ensuring that their behavior matched. He couldn't accept that the universe might allow instant coordination across space, but experiments said otherwise. Over the decades, physicists put entanglement to the test, setting up ever more ingenious experiments first on photons, then electrons, then entire atoms. Each time, the results defied classical expectations. The correlations between entangled partners weren't just strong, they were stronger than anything that could be explained by chance or secret communication. It wasn't trickery, it was reality, wearing a quantum grin. To understand it, you have to stop thinking of particles as little objects and start thinking of them as expressions of a shared wave function. When two particles become entangled, they stop being separate things and start being one combined system described by a single equation. No matter how far apart they drift, that shared equation still governs them both. It's not that one sends a signal to the other, it's that, on some deep level, there is no other. They are one system, stretched across space. Two hands, one handshake, extended through the vacuum. You can picture it like this. Imagine a pair of gloves. You send one to the Andromeda Galaxy, keep one here. The moment you open your box and see a left glove, you instantly know the other is right. That's not mysterious. It's logic. But with entanglement, it's more than that. The gloves don't have a handedness until you look. Your act of measuring one glove creates the property in both, simultaneously, no matter the distance. That's the unsettling part. Measurement doesn't just reveal reality, it helps define it. The two particles aren't communicating, they're participating in the same act of being. You, reading this, are living in a universe where this isn't an exception. It's the rule. Entanglement isn't rare, it's everywhere. Every atom, every molecule, every neuron in your brain is linked by fields that constantly exchange information. You are entangled with the starlight bouncing off your skin, with the breath you exhale into the atmosphere, with the photons that left distant quasars billions of years ago and are only now arriving at your eyes. Quantum mechanics whispers that separateness might be an illusion, a convenient simplification for beings who live at slow speeds and large scales. Underneath, the fabric of existence is woven from connections that defy space and time. Even Einstein's skepticism, poetic as it was, couldn't undo the facts. In 2015, a series of loophole-free Bell tests finally proved it. Entanglement is real, measurable, and unavoidable. The results violated Bell's inequalities, mathematical limits that would hold if local realism were true. The universe, it turns out, is not local. Information doesn't just move. It exists in relationships that transcend distance, and we've begun to harness it. Entanglement now powers the frontiers of technology: quantum computers, quantum teleportation, quantum encryption systems that use the universe's own spooky logic to do things classical physics never could. But beyond the wires and equations, there's something hauntingly beautiful about it. Somewhere, in the dark, two particles that once danced together still move in perfect coordination, their fates entwined forever. No message passes between them, no force binds them, only the quiet promise of their shared origin. Maybe, on some scale we can't yet measure, the universe itself is entangled, every atom, a participant in one vast handshake stretching across the stars. And if that's true, then maybe what we call connection isn't a human invention at all. It's the most fundamental feature of reality, the cosmos's way of saying that nothing, ever, is truly alone. Imagine two particles born together, twins, forged from the same spark of energy in the early hum of creation. For a brief moment, they share a single pulse, a single rhythm, as if the universe itself hummed a lullaby and split the note in two. Then, with a flick of quantum whimsy, they fly apart, racing in opposite directions, tumbling through the cosmic sea. One might drift toward the glowing cradle of a newborn star, the other might wander into the shadow between galaxies. You'd think, at that distance, their fates would be separate, disconnected, independent, forgotten. But the universe, as it turns out, has a peculiar sense of humor. When two particles become entangled, they stop being individuals. They no longer behave like this one and that one. Instead, they become one shared state, two halves of a single, invisible pattern. It's as if reality itself performs a secret handshake, binding them together in ways our logic still struggles to grasp. When we measure one particle, say, its spin or its polarization, the other knows instantly, mirroring the result, no matter how far away it has traveled. No light beam, no signal, no whisper passes between them. It simply is. Einstein, famously allergic to nonsense, called it spooky action at a distance. He hated it not out of stubbornness, but because it seemed to mock everything he believed about how the cosmos should behave. His theory of relativity was built on one sacred law: nothing moves faster than light. Not sound, not thought, not even gossip in a small town. Yet entanglement appeared to break that rule effortlessly, like a magician walking through a wall and smiling afterward. For decades, physicists argued over what this meant. Some said it proved quantum mechanics was incomplete, that there must be hidden variables quietly coordinating the show. Others believed it revealed something deeper, something terrifyingly intimate about the universe itself. That distance is not as absolute as we think. Then came the experiments, elegant, clever, and occasionally nerve-wracking. Photons shot through polarizers, electrons paired and measured, atoms linked across labs. Every test, every trick, confirmed the same unyielding truth: the entangled connection is real. No hidden wires, no cosmic trickery. When you observe one particle, the other instantly reflects that observation, as if they're two sides of a single cosmic coin, tossed once and split forever. But before we crown this phenomenon faster than light texting, it's worth clarifying. Entanglement doesn't allow communication. You can't send messages through it, no matter how tempting the idea of a galaxy-wide quantum WhatsApp may sound. Nothing travels between the particles. No signal, no force, no messenger pigeon. Instead, their correlation is baked into the mathematics of the universe itself. It's not a transmission of information. It's a revelation of relationship. Not faster than light magic, but deeper than space logic. To many scientists and philosophers, this feels like peeking under the universe's curtain. It suggests that the cosmos isn't built out of separate pieces at all, but out of relationships. That space may only be an illusion, a convenient stage on which reality performs. In that light, entanglement is less a communication channel and more a reminder that separation might be the ultimate myth. And yet, for all its mystery, entanglement isn't confined to ivory tower thought experiments anymore. It's now the beating heart of some of our most daring technologies. Quantum computers rely on entangled qubits to perform calculations that would take classical computers the lifespan of stars. Quantum cryptography uses entanglement's eerie precision to create codes that are, in theory, unbreakable. And quantum teleportation, yes, that phrase beloved of science fiction, has already been demonstrated, with particles teleporting their states across distances of hundreds of kilometers. Somewhere, one imagines Einstein rolling his eyes in disbelief, and perhaps, grudgingly, in admiration. His spooky action has evolved from a philosophical headache into an engineering blueprint. But even stripped of jargon and circuitry, there's a quiet beauty here, something almost spiritual. Entanglement whispers that the cosmos may be one continuous whole, that every particle, every atom, every star might still hum in resonance with everything else. Perhaps, on some level beyond measurement, we are all still shaking hands across the void. So yes, Einstein was right to be uneasy. Entanglement is spooky, a ghostly handshake that stretches across the galaxy and ignores every rule of common sense. But it's also profoundly elegant, proof that the universe doesn't draw borders the way we do. The cosmos, it seems, keeps certain things in touch, not by proximity, but by definition. And maybe, in that strange quantum way, the universe is reminding us of something quietly human. That connection is not about distance. It's about belonging to the same story. In the quantum world, Things don't exist the way we're used to. Before we look, they aren't here or there. They're everywhere and nowhere, spread out like whispers of potential. A particle before measurement isn't a point in space. It's a probability wave, a mathematical cloud describing all the places it could be. Then, the moment we measure it, click, the wave collapses. The blur of possibilities vanishes, and a single outcome appears. The electron is here, not there. The cat is alive, not dead. The coin has landed, heads or tails. But the million-dollar question is why? What exactly forces that collapse? Physicists have been arguing about it for nearly a century. Some say observation, the act of measuring, somehow chooses one reality out of many. Others insist the wave function never really collapses at all. It only appears to, from our limited perspective. Still others argue that everything happens, every possible outcome, each in its own separate universe. Whatever the answer, one thing is clear. This collapse marks the border between the quantum and the classical, between maybe and is. The rules of probability rule absolutely until something asks for a result. It's as though reality hesitates, holding all options open until the spotlight turns on, then commits to a single story and sweeps the rest under the cosmic rug. The math works beautifully, but the meaning remains maddening. Does consciousness trigger collapse? Does nature decide on its own? Or is collapse just a trick of perception, our minds trying to fit infinite outcomes into one linear timeline? No one knows for sure. The universe keeps its secret, smiling softly from behind the equations. What we do know is that everything solid, certain, and visible begins as something uncertain, shimmering with possibility. Reality, it seems, isn't built from facts, it's built from choices. Choices that, somehow, the cosmos makes every time someone, somewhere, looks. Let's begin with a paradox, a universe that refuses to make up its mind until you ask it a question. In the quantum world, possibility is more fundamental than reality. Before you look, before you measure, before you even think to wonder, everything exists as a superposition, a shimmering cloud of maybes. Every electron, every photon, every atom of you isn't here or there. It's here and there, everywhere its equations allow, all at once. If that sounds mystical, it isn't, it's mathematical. Quantum mechanics doesn't describe where things are. It describes where they might be. Each particle is governed by a wave function, a kind of cosmic to-do list of probabilities. The wave function doesn't give definite answers. It hums softly in superposition, suggesting all the possibilities that could unfold. Then you look, and the music stops. When you measure a quantum system, observe it, interact with it, force it to declare itself, that smooth, flowing wave of possibilities collapses into a single reality. The particle appears at one location, in one state, as if the universe finally chose a page in the book of what could be. This process is called wave function collapse, and it's one of the most debated ideas in all of science. What exactly causes it? Is it physical? Is it mental? Is it even real? Some physicists say collapse is just a convenient story, that the wave function never truly collapses. We just stop seeing the other outcomes. Others think the act of observation, of gaining information, really does transform the system. The equations don't care how you look. They only insist that once you do, everything else disappears. You could think of it like flipping a coin, except in quantum mechanics. The coin doesn't land heads or tails. It spins forever in a blur of both until someone peaks. And the moment you do, the entire universe conspires to deliver one outcome. What happens to the other one? That's the question that haunts everyone, from physicists to philosophers to night shift dreamers. Where do all those other possibilities go? The particle could have been over there. It could have gone left instead of right. It could have been a wave crest instead of a trough. But when you look, all of those potential versions vanish like mist in morning light. Unless, of course, they don't. Some interpretations, like the many worlds theory, suggest that collapse never really happens. Instead, every possible outcome becomes real, but in separate, parallel branches of the universe. In one world, the particle lands left. In another, it lands right. In another, it never interacts at all. Infinite versions of reality, all equally real, all branching from every quantum event. In that sense, you've never made a decision, you've just slid into one of countless possible yous, while the others continue elsewhere, wondering the same thing. But even if collapse is just an illusion, it's a very useful one. The math works. It predicts everything from the color of atoms to the functioning of semiconductors. When the wave function collapses, reality becomes crisp, definite, measurable. The fog clears just long enough for us to build a world before the haze returns. It's comforting, in a strange way, that certainty is temporary, that we live suspended between knowing and not knowing, in a universe that never fully commits. It keeps us curious. It keeps science alive. Think about that for a moment. Every time you observe something, from a flickering candle to a star in the distance, you are collapsing possibilities. You are making the universe choose a specific outcome from its infinite menu. The cosmos isn't just happening to you, it's happening with you. Each glance, each breath is a collaboration. It makes you wonder, how much of reality is out there waiting? And how much is born the moment you look? Because the wave function doesn't just describe particles, it describes everything. Even consciousness might be woven into that quantum fabric, both an observer and a participant, collapsing the fuzziness of existence into the crispness of now. So, when you look at the world around you, the chair, the window, the sky, remember that what you're seeing isn't the whole story. It's just one version the universe selected in your presence. All the others are still humming softly, just beyond reach, waiting, because at the heart of quantum physics lies a simple, humbling truth. Before you look, everything is possible. After you look, only one thing is. And between those two moments, that breathless flicker of decision, the universe holds its breath, balancing on the edge of maybe. If the idea of the wave function collapsing feels too abrupt, too final, there's another far stranger possibility. Maybe it never collapses at all. Maybe every potential outcome actually happens, just not all in the same universe. This is the many worlds interpretation, and it's exactly as unsettling as it sounds. When you measure a particle, the universe doesn't pick one result. It splits. In one branch, the photon goes left. In another, it goes right. In one world, Schrödinger's cat lives. In another, it doesn't. Each possibility unfolds in its own timeline, as real as yours, drifting away in silence. To us, it feels like chance. We see only one version, one thread of the cosmic tapestry. But beneath that apparent simplicity, reality might be fracturing constantly, branching into countless worlds with every quantum event, every blink, every coin toss, every heartbeat, another division, an infinite family tree of universes, each unaware of the others. It's a beautiful thought, in a dizzying way. Somewhere, another version of you didn't pause this video. Somewhere else, you're still trying to understand the intro. And somewhere far, far away in possibility space, another you has become a quantum physicist, shaking their head at the absurdity of all this. The idea came from Hugh Everett in the 1950 seconds, a graduate student who dared to take the math literally. No collapses, no observers, just one universal wave function evolving smoothly, splitting endlessly into branches that never cross. Most physicists dismissed it at first as science fiction, but over the years, the simplicity of the math and the philosophical elegance of avoiding collapse kept the idea alive. If it's true, then nothing ever truly disappears. Every possibility is realized somewhere. The universe doesn't roll dice, it writes every outcome. And we, the observers, are just passengers on one of its many pages, wondering how many others are being written right now, quietly, beside ours. 17. Quantum tunnels and ghostly leaps. In the classical world, barriers are solid things. A ball can't roll through a wall, a person can't walk through glass, and your car can't casually appear on the other side of a mountain just because it feels like it. But in the quantum world, the rules are far more lenient and much weirder. Particles, it turns out, can simply skip across barriers. Not over them, not around them, through them. This phenomenon is called quantum tunneling, and it's one of those rare things in physics that's both baffling and absolutely essential. Here's how it works. Imagine a particle trapped behind an energy barrier, like a marble in a bowl. Classically, it shouldn't have enough energy to climb out. But because quantum particles aren't just dots, they're waves. Part of their wave extends beyond the barrier, and every so often, that little extension becomes a doorway. The particle doesn't climb over, it appears on the other side, as if reality hiccuped and decided distance was optional. It's not magic, it's math. The probability of the particle being elsewhere is never exactly zero, so, given enough time, it simply is elsewhere. One heartbeat, it's trapped. The next, free. The laws of probability shrug, and physics politely looks the other way. This ghostly leap isn't just theoretical. It's happening constantly, all around you. The sun, for instance, relies on quantum tunneling. The protons in its core don't have enough energy to fuse under classical physics, but tunneling lets them sneak close enough to merge, igniting the light and warmth that make life possible. Even the microchips in your phone depend on tunneling. Electrons jump across barriers in transistors billions of times per second, turning quantum weirdness into practical engineering. Without it, your devices would go dark, and so would the stars. In the end, tunneling is a quiet reminder that the universe is never as rigid as it seems. The walls we imagine between here and there, between possible and impossible, are only as strong as the probabilities that hold them. And in the quantum world, even impossibility leaks a little. In the classical world, barriers are solid things. A ball can't roll through a wall, a person can't walk through glass, and your car can't casually appear on the other side of a mountain just because it feels like it. But in the quantum world, the rules are far more lenient and much weirder. Particles, it turns out, can simply skip across barriers, not over them, not around them, through them. This phenomenon is called quantum tunneling, and it's one of those rare things in physics that's both baffling and absolutely essential. Here's how it works. Imagine a particle trapped behind an energy barrier, like a marble in a bowl. Classically, it shouldn't have enough energy to climb out. But because quantum particles aren't just dots, they're waves. Part of their wave extends beyond the barrier, and every so often, that little extension becomes a doorway. The particle doesn't climb over, it appears on the other side, as if reality hiccuped and decided distance was optional. It's not magic, it's math. The probability of the particle being elsewhere is never exactly zero. So, given enough time, it simply is elsewhere. One heartbeat, it's trapped. The next, free. The laws of probability shrug, and physics politely looks the other way. This ghostly leap isn't just theoretical. It's happening constantly, all around you. The sun, for instance, relies on quantum tunneling. The protons in its core don't have enough energy to fuse under classical physics, but tunneling lets them sneak close enough to merge, igniting the light and warmth that make life possible. Even the microchips in your phone depend on tunneling. Electrons jump across barriers in transistors billions of times per second, turning quantum weirdness into practical engineering. Without it, your devices would go dark, and so would the stars. In the end, tunneling is a quiet reminder that the universe is never as rigid as it seems. The walls we imagine between here and there, between possible and impossible, are only as strong as the probabilities that hold them. And in the quantum world, even impossibility leaks a little. You're not made of equations, but you are made of the stuff they describe. The same particles, the same probabilities, the same shimmering uncertainty that dances beneath everything. You don't notice it, of course. The quantum world hides itself well, but its fingerprints are everywhere, quietly shaping the ordinary. Every chemical reaction that lets you breathe, digest, or dream relies on quantum mechanics. Electrons tunnel between atoms to form bonds. Molecules vibrate and resonate in ways only probability can explain. Even the color of the sky, the way light scatters and paints the world blue, all of it depends on the rules that govern the smallest of things. When you feel sunlight on your skin, you're feeling quantum physics in action. Those photons were born in the sun's heart through quantum tunneling, crossed millions of kilometers of space, and were absorbed by the atoms in your cells. Somewhere in that warmth is a trace of the same uncertainty Heisenberg wrote, about the same dance between knowing and not knowing. It's easy to think of quantum physics as distant, abstract, a language for physicists in lab coats. But in truth, you're living it every second. Your thoughts, your breath, the glow of the screen you're looking at, all emerge from the same quiet rules that govern electrons and light. And in a poetic way, you're a kind of superposition yourself, a blur of possibilities, of breakfast decisions and bedtime thoughts, of past selves and future maybes. Every choice you make collapses the wave of your potential into a single path, just as observation does for a particle. Then, in the next moment, it opens again, another set of probabilities, another universe of what-ifs. So even if you never calculate a wave function or measure a photon, you're part of the same cosmic experiment. The same uncertainty that drives the quantum world is what makes your story possible. Fragile, fleeting, and beautiful, precisely because it can never be fully known. 19. When atoms got personal, for most of history, quantum physics lived comfortably in the realm of thought experiments and chalkboards, a strange corner of theory reserved for physicists who enjoyed confusing everyone else. But then, quietly, the world began to use it. The quantum revolution didn't just rewrite our understanding of the atom, it rewrote civilization itself. Those baffling equations, once dismissed as academic puzzles, became the foundation of everything, from communication to medicine. The weirdness got practical. Take the transistor, for instance, the unsung hero of the modern world. Every computer, phone, and smart toaster you've ever met relies on it. A transistor works because electrons don't behave like neat little marbles. They tunnel, jump, and occupy energy states defined by quantum rules. Without that behavior, your devices would be as silent as a stone. Or consider the laser a triumph of quantum mechanics that began as a joke, a solution looking for a problem, scientists once said. Today, lasers guide surgeries, read barcodes, scan groceries, and stream music through fiber optics. Their perfect beams exist because photons, those quanta of light, can be coaxed into marching in lockstep, behaving like a single, unified wave. MRI machines, too, owe their magic to quantum principles. When you lie in that humming tunnel, what's actually happening is the gentle persuasion of atomic nuclei, tiny quantum magnets to align, relax, and sing back signals that can be turned into images of living tissue. It's quantum choreography on a human scale. Even GPS satellites rely on quantum mechanics to measure time with eerie precision. Their atomic clocks tick so accurately that a single second of drift would throw your location off by kilometers. Without the quantum behavior of electrons in those atoms, the world's navigation systems would simply lose their way. In the end, all the blinking screens, digital voices, and invisible signals around you are proof that quantum mechanics isn't just true, it's useful. What began as a philosophical debate about uncertainty became the engine of modern life. The universe may be built from probabilities, but somehow, those probabilities power your playlists. For most of history, quantum physics lived comfortably in the realm of thought experiments and chalkboards, a strange corner of theory reserved for physicists who enjoyed confusing everyone else. But then, quietly, the world began to use it. The quantum revolution didn't just rewrite our understanding of the atom, it rewrote civilization itself. Those baffling equations, once dismissed as academic puzzles, became the foundation of everything from communication to medicine. The weirdness got practical. Take the transistor, for instance, the unsung hero of the modern world. Every computer, phone, and smart toaster you've ever met relies on it. A transistor works because electrons don't behave like neat little marbles. They tunnel, jump, and occupy energy states defined by quantum rules. Without that behavior, your devices would be as silent as a stone. Or consider the laser a triumph of quantum mechanics that began as a joke, a solution looking for a problem, scientists once said. Today, lasers guide surgeries, read barcodes, scan groceries, and stream music through fiber optics. Their perfect beams exist because photons, those quanta of light, can be coaxed into marching in lockstep, behaving like a single, unified wave. MRI machines, too, owe their magic to quantum principles. When you lie in that humming tunnel, what's actually happening is the gentle persuasion of atomic nuclei, tiny quantum magnets to align, relax, and sing back signals that can be turned into images of living tissue. It's quantum choreography on a human scale. Even GPS satellites rely on quantum mechanics to measure time with eerie precision. Their atomic clocks tick so accurately that a single second of drift would throw your location off by kilometers. Without the quantum behavior of electrons in those atoms, the world's navigation systems would simply lose their way. In the end, all the blinking screens, digital voices, and invisible signals around you are proof that quantum mechanics isn't just true, it's useful. What began as a philosophical debate about uncertainty became the engine of modern life. The universe may be built from probabilities, but somehow, those probabilities power your playlists. If ordinary computers are like disciplined accountants, neat little machines that tick through ledgers of logic, balancing zeros and ones with bureaucratic precision, then quantum computers are more like jazz musicians. They don't march through numbers. They improvise through probabilities, playing every note at once, riffing on uncertainty, and only settling on an answer when the music finally resolves. Instead of bits that are either 0 or 1, quantum computers use qubits, tiny, shimmering systems that can be both 0 and 1 simultaneously, a paradoxical state known as superposition. Imagine flipping a coin and freezing it mid-air. Not heads, not tails, but all possibilities at once. That's what a qubit is doing, spinning in a cloud of maybe, whispering to the universe, let's keep our options open. It's a poetic idea, until you try to build one. Because to make a quantum computer work, you need to convince dozens, maybe hundreds, of impossibly fragile particles to dance together in perfect synchrony, entangled, aligned, and utterly undisturbed. A single vibration from the floor, a wandering photon, a micro degree of temperature drift, even the faint electrical sigh of a coffee machine next door can ruin the entire performance. Physicists call this catastrophic interruption decoherence, but quantum heartbreak feels far more honest. So, the engineers respond with devotion that borders on ritual. They chill their machines to near absolute zero, colder than deep space, because at that temperature, noise slows, atoms calm, and the fragile music of quantum states can play undisturbed. They wrap the processors in layers of gleaming copper and gold, building towering refrigerators that look less like computers and more like alien chandeliers, shimmering columns of cables, shields, and superconducting coils. Standing beneath one, you half expect it to start singing. Inside those glittering towers, the qubits begin their microscopic symphony. Entangled with one another, they don't just test one answer at a time like our classical silicon clerks do. They explore all possible answers simultaneously, a grand improvisation through the landscape of every conceivable outcome. Then, when the measurement comes, the quantum equivalent of the conductor's final cue, the wave of possibilities collapses, and a single note rings out, the correct solution. It sounds miraculous, but it's also heartbreakingly brief. These delicate orchestrations often last only microseconds before the outside world intrudes. In that sliver of time, however, quantum computers can solve problems that would take classical supercomputers longer than the lifespan of stars. For tasks like modeling molecular bonds, optimizing global logistics, or decrypting complex codes, their potential borders on the mythic, a calculation that would take a traditional machine longer than the age of the universe might one day be solved over lunch by a quantum processor, assuming no one sneezes near it. And yet, despite the hype, we're still living in the dawn of the dream. The quantum revolution hums quietly behind laboratory doors. The prototypes are temperamental, their error rates stubborn, their coherence times fleeting. But progress is relentless. Each new generation of qubit, whether trapped ions, superconducting loops, or photonic pulses, brings us closer to that elusive moment when computation truly becomes quantum. It's easy to forget that what these machines do isn't magic. It's nature. The laws they exploit, superposition, interference, entanglement, aren't exotic tricks, but the same rules that have governed the cosmos since the first atoms formed. Every electron in every atom of your body already behaves like a miniature qubit, juggling probabilities until observed. Quantum computing isn't inventing something new. It's finally learning to speak the universe's native tongue. And that, perhaps, is what makes it beautiful. When we build quantum computers, we aren't just chasing speed or power. We're learning to think like reality itself, not in absolutes, but in possibilities. Instead of asking, is it this or that? The quantum mind asks, why not both, until we know? So imagine, for a moment, standing in one of those chilled laboratories. The air hums faintly. The golden chamber glows in the dim light. Inside, billions of probabilities sway together, like reeds in an invisible breeze. Somewhere in that quiet shimmer, the future of computation is dreaming not in binary, but in the language of the cosmos, soft, fluid, uncertain, and infinitely creative. One day, when these machines awaken from their delicate slumber, they may redefine what it means to know, to calculate, to imagine. But for now, they dream cold, quiet, patient, humming the same jazz tune the universe began with, a melody of maybe. For most of the 20th century, biologists and physicists lived in separate worlds. One studied feathers and forests, the other stared at equations and electron clouds. Life, it was assumed, was far too warm, wet, and messy for delicate quantum effects to survive. But nature, as it turns out, is a better physicist than we are. Take photosynthesis, for instance, the quiet miracle that powers nearly all life on Earth. When a photon from the sun strikes a leaf, the plant must move that energy efficiently toward the chemical machinery that turns light into sugar. Classical physics says that should be a chaotic, lossy process. Yet plants manage near-perfect efficiency. How? Evidence suggests that, for a fleeting instant, the photon's energy travels as a quantum wave, exploring all possible paths at once before choosing the quickest one. In other words, your garden is solving optimization problems faster than any supercomputer. Then there are birds, particularly migratory species like robins, who seem to sense Earth's magnetic field, not by metal, but by quantum entanglement. Inside their eyes are molecules called cryptochromes, which react to light by creating pairs of entangled electrons. These pairs act like tiny compasses, sensitive to the planet's magnetic whispers, helping the bird navigate across continents with uncanny accuracy. Even enzymes, the microscopic machines that speed up life's chemistry, may rely on quantum tunneling to make reactions happen faster than classical mechanics allows. Protons and electrons, instead of climbing over energy barriers, simply appear on the other side, skipping steps like subatomic magicians. It's humbling to realize that evolution didn't wait for physics textbooks. Long before humans built particle accelerators, nature was already running quantum experiments in leaves, eyes, and cells. Life learned to borrow uncertainty, entanglement, and tunneling to stay alive, quietly turning the universe's strangest rules into survival strategies. So the next time you see sunlight flicker through a tree, or watch a bird trace its invisible compass north, remember, beneath the feathers and chlorophyll, beneath every breath and heartbeat, the same weird quantum logic that governs atoms is pulsing elegantly, invisibly, and perfectly natural. At the grandest scales, Einstein's relativity reigns supreme. It describes the dance of planets, the warping of space-time, the bending of light around stars. It's smooth, elegant, continuous, a universe that curves but never cracks. Yet, at the tiniest scales, quantum mechanics takes over, whispering that reality is not smooth at all, but grainy, jumpy, built from flickering probabilities. Each theory works flawlessly in its own domain, but when you try to make them sit together, the math bursts into flames. This uneasy truce between the large and the small has haunted physics for a century. Relativity insists that gravity is geometry, the shape of space-time itself. Quantum theory insists that everything, including space and time, should be uncertain, fluctuating, fundamentally fuzzy. So what happens when you zoom in close enough to where the curvature of space-time meets the jitter of the quantum world? Nobody knows. That's the problem of quantum gravity, the greatest missing manual in science. Physicists have tried to bridge the gap with a dozen grand ideas. String theory imagines that the smallest bits of matter aren't particles, but vibrating loops of energy, tiny strings, whose harmonies create everything from quarks to galaxies. Loop quantum gravity takes a different route, suggesting that even space itself is made of discrete chunks, atoms of geometry, woven together like fabric. Both theories are elegant, both could be right, and neither has yet been proven. Part of the challenge is that we can't easily test these ideas. The scales where quantum gravity becomes obvious, where space-time truly unravels, are far beyond any laboratory we can build. We catch faint clues in black holes, in the early universe, in the subtle tremors of space-time itself, but the full picture remains out of reach. Still, the dream persists, a single framework that describes everything, a universe where probability and geometry finally share a lunch table. Somewhere in the math, hidden like a note between worlds, lies the recipe for reconciling Einstein's cosmos of curves with Planck's universe of quanta. Until we find it, the universe remains bilingual, fluent in both the language of certainty and the dialect of doubt. Every journey into the universe begins with curiosity, and this one ends where curiosity itself starts to lose its footing. The Planck scale is the ultimate boundary of smallness, the line where all our equations, all our elegant theories, and all our human intuition quietly throw up their hands and whisper, "We don't know." To reach it, you'd have to shrink reality by impossible magnitudes. Start at the size of a human, then an atom, then a proton, and keep going. Smaller than quarks, smaller than anything you've ever heard of, down to a scale about 10 to the power of negative 33 centimeters, the Planck length. It's so tiny that if an atom were the size of the observable universe, the Planck length would still be smaller than a tree on a distant world inside it. At that level, the universe stops behaving like a smooth fabric and starts looking like static, a wild, foaming sea of quantum fluctuations. Space-time itself no longer acts continuous. It writhes, ripples, and tears in a dance of probabilities so violent that even the concept of before and after begins to wobble. Einstein's graceful geometry of space-time can't handle it. Quantum mechanics can't either. They both stutter, contradict, and break. Some physicists think this is where gravity becomes quantum, where space itself might come in tiny, discrete chunks. Others imagine microscopic black holes popping in and out of existence so quickly that reality becomes a flickering mosaic of collapsing horizons. It's the basement of the cosmos, the point where physics, like a nervous host, starts fidgeting with the keys and pretending the party's over. Below this scale, our best tools, math, measurement, even metaphor, stop working. We can't describe what happens, not because we haven't looked hard enough, but because looking itself stops having meaning. The Planck scale isn't just small, it's foundational. It's the place where the universe might be coded, where everything above it, from galaxies to thoughts, is written in a language we've only begun to glimpse. It's the final riddle of scale, not just how small things can get, but whether small even exists at all. What if quantum mechanics isn't just about atoms and particles, but everything? What if the entire cosmos, from galaxies to grass blades, exists as one enormous wave function, humming softly across space-time, still waiting for its final observation. It sounds like poetry, but some physicists take the idea seriously. In this view, the universe itself is a quantum system, a single, entangled whole. Every star, every photon, every thought in your mind isn't an isolated event, but a note in a cosmic chord, resonating with everything else. When you observe a particle here, you're not merely changing its state, you're touching the entire universe, ever so slightly. It's a perspective that turns reality inside out. Instead of the universe containing quantum systems, maybe quantum systems contain the universe. The wave function of all existence spreads across infinity, a mathematical object too large for comprehension, describing not just where matter is, but where it could be. Everything, everywhere, all at once. If that sounds philosophical, it's because it is. Quantum cosmologists like Hugh Everett, John Wheeler, and more recently Sean Carroll have wondered, if observation collapses a wave function, who or what observes the universe itself? Does the cosmos collapse its own possibilities? Or does it remain forever suspended infinite, uncertain, half real, until something outside it takes notice? Maybe there isn't an outside. Maybe observation is baked in every interaction, every exchange of energy, every star that warms a planet is the universe observing itself. You, right now, listening to this, are part of that experiment, a self-aware ripple in the grand wave function, briefly noticing itself before dissolving back into the whole. It's a dizzying idea that everything we call real might be just one outcome in an infinite quantum superposition. The cosmos as a single, uncollapsed equation, vast, entangled, alive with probabilities, and us, tiny but conscious, playing our fleeting role as witnesses to a reality still being written. 25. The end of certainty. After a century of experiments, paradoxes, and equations scribbled in chalk and starlight, quantum physics has given us miracles: lasers, transistors, MRI scans, computers, and yet, not peace. It has not restored certainty. It has undone it, beautifully. At the smallest scales, the universe refuses to be pinned down. Electrons exist in maybes, photons play both sides, and even nothing hums with possibility. The harder we try to define what's real, the more reality slips through our fingers, as if laughing gently at the arrogance of measurement. The quantum world isn't chaotic, it's indifferent to our need for neatness. It doesn't care for tidy answers, only probabilities that shimmer like candlelight. And perhaps that's the quiet lesson. Science isn't about declaring truth in stone. It's about learning to live inside uncertainty, to stand in wonder while the numbers whisper their secrets and the equations hum their soft music of maybe. The universe doesn't owe us clarity. It offers mystery, and somehow that's enough. Because when you look closely, close enough to see atoms breathe and particles blink, you begin to realize that certainty was never the goal. The goal was awe. The kind of awe that built telescopes and theories, cathedrals and questions. The kind that reminds us we are not separate from the strangeness, but made of it. So the next time you reach for something solid, a wall, a hand, a thought, remember, it's all built on uncertainty, held together by probability, illuminated by curiosity. And maybe, just maybe, that's the most reassuring thing of all, that the universe doesn't need to make perfect sense to be perfectly beautiful. After a century of experiments, paradoxes, and equations scribbled in chalk and starlight, quantum physics has given us miracles: lasers, transistors, MRI scans, computers, and yet not peace. It has not restored certainty. It has undone it beautifully. When Einstein first declared that God does not play dice, he was not being poetic, he was protesting. Quantum mechanics had arrived, gleaming and ghostly, with its probabilities and paradoxes, and it offended his sense of order. He wanted a universe of cause and effect, not of chance and whispers. But the dice, it seems, were real, and they were rolling all the time, in every atom, every photon, every flicker of existence. At the smallest scales, the universe refuses to be pinned down. Electrons exist in maybes, photons play both sides, and even nothing hums with possibility. Empty space isn't truly empty. It seethes with virtual particles that pop in and out of existence like thoughts you almost remember. The harder we try to define what's real, the more reality slips through our fingers, as if laughing gently at the arrogance of measurement. We've built machines to trap light, to time atomic decay to billionths of a second, to peer into the heart of uncertainty itself, and all they've told us is that nature is less like a clock and more like a dream. And yet, this uncertainty is not chaos. It's a kind of cosmic improvisation, the universe riffing on themes of probability and potential, weaving existence out of equations that don't quite settle. The quantum world isn't unpredictable because it's wild. It's unpredictable because it's profoundly subtle. It doesn't care for tidy answers or neat boundaries. It only offers probabilities that shimmer like candlelight, soft and wavering, illuminating just enough for us to keep wondering. Perhaps that's the quiet lesson hidden in all the math. Science isn't about declaring truth in stone. It's about learning to live inside uncertainty, to stand in wonder, while the numbers whisper their secrets and the equations hum their soft music of maybe. It's about daring to look at the fog and say, there's something here worth understanding, even if we never see the edges. The universe doesn't owe us clarity. It offers mystery, and somehow, that's enough. Because when you look closely, close enough to see atoms breathe and particles blink, you begin to realize that certainty was never the goal. The goal was awe. The kind of awe that built telescopes and theories, cathedrals and questions. The kind that humbles you, then hands you a pencil and says, try again. Every experiment, every discovery, every revelation is a love letter written in uncertainty, an admission that we don't know. And that's why we keep looking. Quantum physics reminds us that we are not separate from the strangeness, but made of it. Every atom in your body obeys the same shimmering rules as the ones in a star. You are a statistical miracle, a pattern of probabilities held together long enough to wonder what you're made of. Somewhere inside you, particles are tunneling through barriers, existing in two places at once, vanishing and reappearing with cosmic indifference. You are, in every sense, quantum poetry, uncertain, temporary, magnificent, and maybe that's the most human thing of all, to seek certainty in a universe that doesn't offer any, to build meaning in the gaps, to write symphonies on the edge of probability. When Schrödinger imagined his infamous cat alive and dead, both and neither, he wasn't just toying with paradox. He was reflecting us. We are that cat, caught between knowing and not knowing, alive in our curiosity, suspended in possibility. So the next time you reach for something solid, a wall, a hand, a thought, remember, it's all built on uncertainty, held together by probability, illuminated by curiosity. The atoms in that wall aren't fixed. They're vibrating clouds of chance. The hand you hold is a dance of forces and fields, never the same twice. Even your thoughts are probabilistic, electric storms of neurons flickering in quantum-sensitive chaos. And somehow, through all that, meaning emerges, connection forms, life continues. In the end, certainty was never the prize. The prize was participation, to be part of a universe that doesn't make perfect sense, but insists on being perfectly beautiful. To learn to love the maybe, to rest inside the question, to drift through the grand experiment with open eyes and a quiet heart. Because if you listen closely enough in the silence between equations, in the hum of space itself, you can almost hear it. The laughter of the cosmos, soft and amused, as if whispering, "You were never supposed to be certain, you were supposed to be amazed."